All right, we're back. We're going to be on page 106 of Math Analysis Notes 10, which is about solving triangles, non-right triangles, so oblique triangles. But what I want to do now is I want to take a look at the scenario we're about to talk about, which is called the ambiguous case. We're going to use GeoGebra. I put together these things. This is called the ambiguous case of the law of sines. So in this case, and the reason we're doing it here is that if you look at it dynamically, so you watch it move, it's way easier to remember how this works. And actually, I kind of like always think of how it like physically will interact with the world to figure out how many triangles I can get. Will there be triangles? Let's take a look at it and just see. So this, you actually can get to this. I don't know if I have a link to it anywhere, but I think if you type in geogebra.org/m/cbjdbtfq. So rewind the video and get that again if you want it. I think it'll take you to this, and I think you can play around with it. And playing around with this is a pretty good way to understand it. So let's take a look at what we're dealing with. So here's a basic idea. You are given, right? So there's always a set of givens, right? So we know that if we have angle, side, angle, 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 side, solve it. Law of sines, just gonna work. So that was, we have an angle side pair. That's the essential thing. If you know like angle A and side A, law of sines. If you know angle B and side C, angle B and side B, I don't know what I said, B and B, law of sines. Here's a scenario where we are given angle A, so it's given. We are given side A, right? The side opposite angle A. And then we're given another side. So we actually have a side angle pair. So it's a law of sines problem, but we don't have another angle. So there's a little more ambiguity here. Like, what's going on? Well, it turns out that if I take this and I just start like moving it around, do you notice what doesn't happen? This side never connects with the horizontal line that is determining our given angle, right? Our given angle is between this horizontal line and this other given side. So this angle is given. This length is just not long enough. So in this case, and so this is always, this feels cheap. This is a set of given information. It is an angle, the side opposite that angle, and another side. It is angle, side, side. It's a case where you might be able to use the law of sines. There's no triangles. So my explanation here, the side opposite the given angle is just not long enough to reach the horizontal. You're never going to get a triangle. So this is a given set of information. It fits the criteria of using the law of sines, but there's no triangle. It's not long enough. So why isn't it long enough though? Well, if you look at this, for this side that's kind of going back and forth to be long enough, it would have to be longer than the height that I'm kind of indicating right now with the mouse. It would have to be longer than this height, or at least as long as that height, which would give you, if it was exactly as long as that height, you would get one right triangle. And it'd be a miracle because what are the odds? But you would get a right triangle. In this case, it's just too short, right? So it's not bigger than the height of the right triangle that we would determine here. If it's not bigger, if it's shorter than the height, zero triangles. So this is our zero triangle scenario. So it is a set of given information that kind of works, but it doesn't work. So I'm going to stop the motion here. So that's one possibility. And I think there's a way for me to get to the next thing at the bottom here. Yeah. So if I go here, go next. All right. So let's change it up a little bit, just a little bit. You can see we have an angle, which is given. The side opposite that angle is given. So angle, side opposite the angle, that's law of sines. But then we don't know another angle. What we know is another side. This is more annoying. So we're given this. I always draw it this way with a given angle here. The side opposite the given angle is just kind of hanging out, right? Like just this thing that's going to like go back like a pendulum, I guess. And then the other given side, I'm always going to put here. So I'm always going to draw it that way. And when we do the problems in the notes, you'll see that I always draw it that way. Not really ambiguous. It takes all the ambiguity out of the ambiguous case. So let's see. I'm going to start the motion and see what happens. There's a triangle. And that's it. There's a triangle. And there's a triangle, but same one. That's it. We do get a triangle though. So let me stop this. So this is long enough. It's longer than the height. Gives us a triangle right there. It connects. But then it just swings through and it never connects again. But what's the key here? So It's definitely longer than the height. Like if I put it here, you can see it's way longer than the height, right? So if this side that's moving had been shorter than the height, 0 triangles, it never connects with the horizontal, it's just not gonna work out. Here it's longer than the height, so we're definitely gonna get a triangle. It's definitely gonna connect, connects right here. It doesn't connect again though. Like, can you conceive of a scenario where this swings through and is short enough that it connects again, right? Like the intersection point, like here. This could have worked if our side opposite the given angle had been exactly the length from B to this intersection point. We would connect here, and we would have connected like over here, kind of symmetrically. But in this case, it didn't happen. And the reason it didn't happen was when I get all the way over here, it turns out that the side opposite the given angle, right? So given angle, side opposite the given angle. The side opposite the given angle is actually longer than the other given side. So when that happens, we will get one triangle for sure, but that's it. We're just gonna get one triangle. So if the side opposite the given angle is longer than the other given side, we get one triangle. And that's probably the explanation I gave here. So the side opposite the given angle is long enough to reach the horizontal. You get a triangle. If it continues to swing through though, it will never connect again. And so you do not get another potential triangle. You just get the one that you get, which is fine. Like there's nothing wrong with that, but there is a triangle in this case. So if the side opposite the given angle is bigger than the other given side, you're gonna get one triangle. Let's scroll down and take a look at the third scenario. All of these, by the way, I should say, are if the given angle is acute. If it's obtuse, it's like slightly different, but it's a lot easier. So I didn't even bother making a GeoGebra thing for that. So let's see here. So here is the third scenario. So in the third scenario, this doesn't look like the third scenario to me, but we'll find out. I'm gonna start the motion. Oh, look at that, wow. When I was like eyeballing it, I was like, I thought the side opposite was gonna be shorter than the height. Like it really looked like it was going to be, and I was like, oh no, there's gonna be no possible solutions. But no, here we go. So the side opposite is longer than the height, which is why we're connecting with the horizontal, right? If it was shorter than the height, we would never connect with the horizontal, we would get no triangles. It's longer, so we're gonna get a triangle for sure, like in the previous one. But in this case, there's an interesting relationship. So let me stop it so I can kind of talk about it more briefly or more succinctly or more something. So here, at this point, you can see side opposite the given angle, right? So given angle is here, it's angle A. Side opposite the given angle is bigger than the height of that would-be right triangle, right? So it's bigger than the height, so you get a triangle. It's also, the side opposite the given angle is also shorter than the other given side, which means that after you connect once because you're bigger than the height. After you connect once, you will swing through and connect again and create a second potential triangle. So this is what most people think of as the ambiguous case. It's crazy, 2 triangles. With this given set of information, you could get 2 triangles. So if you hired someone to build you a triangle with this particular given set of information, right? So you have an angle, side opposite the angle, another given side. But you do this weird thing where the side opposite the given angle, right? The side opposite the given angle is bigger than the height of the would-be right triangle and shorter than the other given side. If you don't give the person building your triangle very specific directions, you could get 2 different triangles back. One of them over here is, it's whatever, it's triangle. There's nothing super special about that. This triangle, or you could actually, so I guess what I was gonna say is that this is an acute triangle. Is that right? Acute triangle, all the angles are acute. Like there are no obtuse angles. So this is an acute triangle. If you swing through, there's actually an obtuse triangle that you could also get where this angle opposite the other given side comes out obtuse. How does this happen? This happens because, think about sine, right? Sine in the first quadrant, so for angles between 0 and 90 degrees in the first quadrant, is positive. Sine in the second quadrant for angles between 90 and 180 is also positive. There are 2 angles that satisfy sine of blah is equal to 0.3, right? There's 2 angles one in quadrant 1, one in quadrant 2 that satisfy that. And the law of sines doesn't really tell you which of those you're supposed to have. So this is the 2 triangle case. So we're going to go to the notes in the next video and like look at this more concretely, but this is what's happening. So in these scenarios, the first thing that you want to do is you want to know what you're dealing with. So you basically draw a picture that kind of looks like this, right? So you'll have your angle that you know, the side opposite that angle, and you just draw it so it's like dangling in the air, and then another given side, which is always going to be here. Now you think, is the side opposite the given angle bigger than the other given side? In which case you just get one triangle, you use a law of sines, you solve it, awesome. If it is not bigger, now you have to calculate the height, because now maybe there are no triangles. So we're going to calculate the height. After you calculate the height, you see, is the side opposite the given angle bigger than the height, right? Is this happening? Because if it's bigger than the height and it's less than the other given side, you have 2 triangles. If it's smaller than the height, you have no triangles. So the thought process, and it's in the notes, is immediately look, is the side opposite bigger than the other given side? If yes, 1 triangle. If it is not, calculate the height. Is it bigger than the height? If the side opposite is bigger than the height, 2 triangles. If the side opposite is smaller than the height, no triangles. And that's it. So I'm going to come back in the next video, and you can play around with this. I think you should play around with this until you like totally make sense of it. Let me see what this says. Oh, look at this. We can see the triangles. Okay, so the side opposite, I don't remember when I make these things, who even knows? The side opposite the given angle is 2 things. It is long enough to reach the horizontal because it's longer than the height, and it is not so long that it won't hit again before swinging through. It is shorter than the other given side. So it's between, it's an inequality. You have height, side opposite, other given side, right? So if it fits that, then you get 2 triangles. So one of them is the big triangle, which is acute, right? So it's weird because the big triangle is the acute one by angle measure. So you get this, that's your big triangle. That's the first place that you hit. I remember making this. This was a pain in the neck to make. And then there's a small triangle. The small triangle is obtuse, right here. And now I think that if I show them both at the same time, you see something kind of interesting. You probably see it. So here, right, this side hits here, this side hits here. This weird triangle is isosceles. That's not one of the triangles that we're going to solve for, but it's an isosceles triangle. And that's really interesting. The law of sines is going to give you this angle, right? You're going to set it up, use the law of sines. You're going to find this angle, the acute angle. But this, because it's an isosceles triangle, this angle and then this angle are the same. And if they're the same, that means that this angle, the obtuse angle in the small triangle, this angle is actually the supplement of the angle that we found here. And that's the key. That's the key to solving these. But anyway, I'm going to stop this here and come back in the next one. We're going to actually do some stuff. So I will see you in that one. The ambiguous case is pretty exciting. So I hope that this made some sense. I hope you play around with it. And I will see you in the next video.